But there's a theory that one of the reasons dinosaurs grew to be so large, and why no terrestrial animals nowadays are nearly as large as the biggest dinosaurs were, is because oxygen levels were much higher back in their day. Oxygen is important in biochemical reactions that provide lots of energy for your body. The more energy, the story goes, the bigger you can become. We're not certain whether or not higher atmospheric oxygen levels are actually the reason as to why the dinosaurs got that big. What is certain is that just like scientists have ways to approximate oxygen content in the Earth millions of years ago, they also have ways to estimate oxygen levels in your blood. This is very important when it comes down to determining why it is that you may not have enough life-giving oxygen within your body. One of the things that blood tests can measure is known as the arterial partial pressure of oxygen, abbreviated as PaO2. For our purposes, what I want you to know is that when someone refers to the partial pressure of oxygen, also known as oxygen tension, they are talking about the amount of dissolved oxygen molecules freely floating about in the blood. The higher the partial pressure of oxygen, the more oxygen will be dissolved in blood. Or, to put it another way, the higher the concentration of dissolved oxygen there will be. As an easier example, I like to think about how soda bottles have tons of those little bubbles dissolved within it. The soda is like our blood, and the gas molecules dissolved within it are obviously the bubbles. These bubbles are represented by PaO2. The normal partial pressure of oxygen in a human is about 75 to 100 millimeters of mercury, and it refers only to the free oxygen within the blood, meaning the type that isn't bound to hemoglobin, the oxygen-carrying molecule located within red blood cells. This value amounts to about 2% of total oxygen content in our blood. Normally, as PaO2 rises, SaO2, or oxygen saturation, will rise as well. Oxygen saturation of arterial blood has a normal range of 94 to 100%. What this means is that normally, 94 to 100% of oxygen-binding sites, which are located on hemoglobin, are saturated with oxygen. Note how that neither PaO2 nor oxygen saturation tell you how much total oxygen is in the blood. Another way to view oxygen saturation is to think about how sponges work. If you take that soda bottle from before and pour it onto a sponge, the sponge becomes saturated with the gas bubbles that were freely floating around before. In the real world, the freely floating oxygen molecules in blood saturate the hemoglobin in a similar fashion. To help remember the difference between PaO2 and SaO2 for the rest of this lesson, since I use both terms interchangeably to get you used to them, here's a little memory aid. PaO2 measures the oxygen that has passed through the lungs and into the blood. SaO2 measures the oxygen that has saturated the red blood cells after oxygen has passed into the blood from the lungs. What I also want you to know is that the PaO2 depends on the partial pressure of oxygen that is inspired from the air within the lungs, termed alveolar PO2, as well as the health of the lungs themselves. If the air is thin, think Mount Everest, or the lungs cannot take in oxygen appropriately due to any number of diseases, then obviously little oxygen gets into the lungs, into circulation, or both, thereby decreasing arterial partial pressure of oxygen. In this case, our blood becomes like a low carbonated beverage. There aren't many bubbles floating around in those either. After oxygen has entered and dissolved within the blood, then and only then can oxygen bind to the hemoglobin in our blood. It is SaO2 that measures oxygen saturation of hemoglobin, and it should be clear that it depends on the partial pressure of arterial oxygen. if P little a O2 drops, there's less dissolved oxygen, and therefore less saturation of hemoglobin with oxygen. Basically, if you use a low carbonated beverage and pour it onto our sponge, obviously the sponge will have fewer bubbles within it than had we used a highly carbonated beverage. But oxygen saturation is tricky. If all of a sudden someone loses a lot of hemoglobin, as long as PaO2 remains the same, so will oxygen saturation. That's because oxygen saturation measures the percentage of oxygen binding sites occupied by oxygen on any and all remaining hemoglobin, not the total amount of oxygen bound to hemoglobin. Therefore, for our needs, remember that both oxygen saturation and the partial pressure of oxygen in arterial blood are independent of the amount of hemoglobin in the blood. By the way, the most common cause of decreased PaO2 is something known as ventilation perfusion mismatch. The decreased PaO2 as a result of VQ mismatch results in hypoxemia, which is a term for decreased levels of oxygen in the blood. This term should not be confused with hypoxia, which is the improper oxygenation of tissues. They are not the same. You may be hypoxic, but not hypoxemic. For example, in cases of anemia, the PaO2 is just fine because the lungs aren't sick. But because our levels of red blood cells or hemoglobin are low, not enough oxygen is getting delivered to the tissues, resulting in hypoxia. Finally, to get a measure of how much oxygen, quantity-wise, is in the body, we have to look to CaO2, or oxygen content, for which we can use a formula that takes into account PaO2, SaO2, and hemoglobin. C(a)O2 measures both the bound to hemoglobin and unbound free oxygen molecules in blood. By this logic, it should be clear that hemoglobin content and both PaO2 and oxygen saturation influence oxygen content. Therefore, in a prior example where someone loses their hemoglobin, the PaO2 and SaO2 will stay the same, assuming normal heart and lung health and oxygen concentration in the environment. But because the amount of hemoglobin has decreased, the total content of oxygen in the blood will decrease as a result. Approximately 98% of oxygen is found bound to hemoglobin in blood, and that is why determining oxygen content, which is highly dependent on total hemoglobin content, is so critical. Okay, it bears repeating that C(a)O2, or oxygen content, measures both the bound to hemoglobin and unbound free oxygen molecules in blood. It is therefore dependent upon S(a)O2, or oxygen saturation, and the arterial partial pressure of oxygen, abbreviated as P(a)O2. The most common cause of decreased PaO2 is something known as ventilation perfusion mismatch. The decreased PaO2 as a result of VQ mismatch results in hypoxemia, which is a term for decreased levels of oxygen in the blood. This term should not be confused with hypoxia, which is the improper oxygenation of tissues.